using charge density based approach. We will see why it is so important. And so DFT, it is basically like it's based on these theorems. There are two theorems which are given by these two people, Hohenberg and the Cohen. And we will see how these two theorems have actually helped Cohen and Sham later to develop a formalism of DFT. And then we will see what is the exchange correlation energy. And then finally, we will see what is the self-consistent cycle, how like the Cohen-Sham equations, they can be solved. Okay, so let's begin. So this is the Hamiltonian of a system where let's say you have m number of electrons and they are all interacting. Okay, so yesterday we saw that the first term is the kinetic energy term of the electrons, and this is the potential, which is because of the nuclei. So if you have, let's say, some n number of nuclei, so in the presence of those nuclei, the electrons are moving. Okay, so we have to write the potential for that, and this is the Coulomb energy repulsion term, which is due to the, let's say, the ith electron, it is interacting with the jth one. So you have to sum over all the pairs, whichever is possible. And this 1/2 is so that we don't double count. And we saw that if we, in principle, solve the Schrödinger equation, many-body Schrödinger equation, in principle, if we find this thing and this thing, we are done. So this wave function is actually your many-body wave function. So this actually tells you, it actually wave function doesn't tell you anything. So it's the square of the wave function, which actually gives you the probability of finding a let's say the electron number 1 at rth position and the electron 2 at r2 position, and so on, and simultaneously, I mean. And we saw that in Hartree or Hartree-Fock equations. So the basic principle that they use, that is called variation principle. They find out, like, you know, the Hamiltonian, and if you know the wave function. So what Hartree did is he actually took independent things like this. So if you have, let's say, m number of electrons, he wrote the wave function like this. So product wave function. Then the Fock came, he realized that this doesn't have the Pauli exclusion principle inbuilt. So he gave another wave function, which we called like Slater determinant, which you can
There's some problem with the network.
Your potential energy curve. Okay, so where if you go with the Hartree, you are able to reach somewhere here. If you go with Hartree-Fock, you are able to reach somewhere much below. So the point essentially I want to make is this. So based on your wave function, you are able to get the energy value. Okay, so by that I mean the energy it's a functional of psi. So in order to explain the word functional, I'll go to the next slide and tell you what is the meaning of it. So we all know what is the meaning of a function. So function is something which takes input, which is a number, and it delivers you an output, which is also a number. For example, this is f of x. Let's say 3x squared is your function. So this is the input I'm giving. If x is 3, so it gives you an output, which is also a number. So some function is something which takes input as a number and delivers you output as a number. Now the functional is little different. So what it does, it takes the function as an input and it delivers you a number. Okay, so what I'm showing here is an example of a functional. Here you see you have an input here, which is, let's say, 3x squared. Now if you integrate this whole thing, you will get x cubed, and if you put the limits, you will get value 8. So this is basically, it has taken the input here and it has given you the output. So the functional meaning something which takes input as a function. So input is function and the output is a number. So this is what you find in the total energy. So energy you can write as a function of charge density, or you can write it as function of functional of wave function. So basically, see this thing, your charge density, that is actually a function. So energy, it's a number. Okay, I hope you got the meaning of it. So let's jump to the next one. So why charge density is so important? So we saw that if you solve the Schrödinger equation, like we have seen yesterday, so basically you get the wave function, which so this R1, there are actually 3 variables, X1, Y1, and Z1. So it means if you have m dimensional, like m number of electrons, you will have 3m variables. Okay, so, and similarly, the wave function itself is a very complex, it's a complex function, so it has no physical meaning. But if you take the square of it, it may have some meaning. So it will tell you what is the probability of finding a electron at R1 and simultaneously the second electron at R2 and so on. Whereas if you look at the charge density, so it is only a variable of three quantities, okay, x, y, and z. So and if you see, it has a physical meaning also. You can actually measure the charge density of any system if you use like those experiments from XRD or something. So this is a measurable quantity, okay? So now this is the thing which they realized, the Cohen and Sham, that instead of using wave function, why not use something which is much more trivial? So yesterday we saw that if you want to store a number, something like this, so you need actually 26, let's say for the iron atom, you need at least something like these many entries. So which is very difficult again. Whereas here you have only three variables, so it is much more easy computationally. Like it is easy to store it. So now this is an example where I'm showing you the charge density of the silicon bulk system, where you see this is the radial, I'm plotting the radial charge density. So this is for the core portion, this is for the valence one. So this is the, like these are your silicon atoms here, and this is the charge density around it. So the other gray curves which you are seeing. So that is actually, you can see it's a measurable quantity. So, but can you imagine something like wave function, what it will do? So you can't imagine, right? Because it's a complex quantity and it has no physical meaning. So it is more intuitive if we progress like something using charge density. Okay. Okay, let's focus on the two theorems. Those are given by Hohenberg and Cohen. So the theorem number one says, so before we go ahead, I just would like to remind you that the Hamiltonian that we wrote, there we had kinetic energy term and we had a potential term, right, which is because of the nuclei. And there is something that is the, you can call it EVV, which is due to the electron-electron interactions. So I'm bothered about this term now. So the theorem number one, it is concerned with the V external or the V due to the nuclei. So what it says that if you have a system of interacting particles, let's say n number of electrons, they're interacting and they're moving in an external potential V. And now they say that if this is uniquely determined, V external, it also determines uniquely the charge density, the ground state charge density, or vice versa. So this is what I'm trying to point out here, that if this is, so if you know the exact charge density for the ground state, you also know what is the external potential, or the vice versa. Both are like work in either way, it works. So now you can actually prove this theorem by the proof of contradiction. So basically you start with the two different V external 1 and V external 2, and you see they will both try to give you the same charge density. So this you can prove. There is no need to prove as of now. We just need to know that there is a charge density. If we know this charge density, this is determined. Okay. Let's move to the theorem number two. Theorem number two says, okay, so it says that, let me just read it later. So let me explain what I'm writing here. So you see, there are three terms: kinetic energy term, V external or E external. Now I'm writing in terms of energy, so it's energy, E, not V. And this is the electron-electron interaction. So this is your total energy of the system, which is a functional of charge density. Now, what this theorem says, that there is a unique functional for this term, En, okay, which depends on the charge density. Now, if, for example, it says that if you somehow determine this thing for the ground state, if I put it here, so if your this density, it corresponds to the ground state density, that is the only density which will minimize this function. This is what the theorem says. Let me read it for you. So a universal function for the energy in terms of density can be defined for a given V external. So see, if you change the V external, it means you are talking about some other different material. Okay, so for a fixed material, so your V external is fixed. So for a given system, there exists a unique functional which can be minimized using ground state charge density. So this is what I'm trying to point out from this graph. If you see, this is sort of a potential energy curve, where see you are let's say this is a blind man, so he's trying to find out where is the minima. So the variation principle is actually telling you if you minimize this, the minimum which is here, that is your the ground state value. So this is what I actually tried to explain earlier. What is the the what do we mean by functional? So here we have energy, which is a function of the charge density. If you get the somehow get this number which corresponds to your ground state density, then you will get a number which is the ground state value, okay, of the energy. Now you can also you see this thing is very trivial. This is determined. Just assume that it's determined. It's very trivial. This is because of the nuclei. So what is not known is the kinetic energy term of the interacting electrons, and this is the 1 over ri minus rj term, right? This is not determined. So these are the two complicated things. You can actually write them as just f. So HK is for the after the name of these two people, Hohenberg and the Cohen. So they call this FK. So what the theorem is actually trying to tell you, that there exists a functional, but they don't give you the recipe how to find these terms. So they are just telling you that there is a functional, and if you try to get the charge density of the ground state, and if you put it here, it will minimize this number, but they don't give you the recipe. So now, in 1965, Sham came. He was the postdoctoral fellow of Cohen. So he actually saw this thing. So he came out with a very unique idea. So the idea is the following. So if you see this figure, this is your these are the electrons, okay, and they are all holding their hands. It means that they are interacting. So one electron is influencing the other one. That ith is interacting to jth, and jth is to kth, and so on. So they are all interacting. So what Sham actually proposed, or the Cohen Sham, both of them approached, like they proposed that let's consider a system where the electrons are non-interacting. So they are individual. They have nothing to do with each other. So this is alone, he's alone, he's alone. They are all alone. Okay. And whatever is left, so the effects which we have to count, let's say the exchange, because if you exchange two fermions, you get to have a wave function which is antisymmetric. Your wave function must pick up a negative sign. And the correlation, by correlation, what I mean, see, if this guy moves, it will also affect him, right? Because they are connected. Okay, so that is the correction which we'll add here, the exchange and the correlation. So instead of dealing with the system of interacting electron, let's deal with the system where you have n number of electrons which are non-interacting, and whatever the correction which I have to add, I will add here because of the exchange and correlation. So in principle, this will give you exact ground state and energy if you solve the your Schrodinger equation. And similarly, if you follow his approach, you will get the same charge density and the exact energy. Okay. So now let's see how they have done it mathematically. So this we have already seen. So the Hamiltonian had three terms: the kinetic energy term, your external potential, your electron-electron interaction. So because of that, we wrote three terms here. One is this is the kinetic energy term for the interacting people, right? The electrons which are interacting. So this is the external potential due to nuclei. This is the Hartree, not the Hartree term, but the electron-electron interaction, which is associated with this thing, Ri minus Rj, which we still don't know what to do about it. Okay. Now, what Cohen and Sham did, so they said, let's forget about this. Let's just talk about non-interacting particles. And so for the non-interacting particle, it is very, very trivial to write the kinetic energy term. See, so these are the n number of electrons. They are moving around freely, independently, nothing to do with each other. So I can write the kinetic energy term for them. So you please note that these two terms are not equal. Okay. So this is the kinetic energy term when they are interacting, and this is the kinetic energy term when they are non-interacting. And these terms are equal. Okay. And this term is the your electron-electron interaction, and this is how we actually try to count them. So what is this? This is the Hartree term, which is the average counting. Yesterday we told that, we came to know that it's just a classical picture where an electron cloud, or the, let's say, the charge density, it is averagely interacting with the other charge density, right? So whatever is left by that, I mean whatever the many body effects are left. So I will include all of them in this new term, which is unknown to us. We don't know it as of now. Okay. And if you take this functional, if you take instead of taking the equation 1, if you take equation number 2 and if you minimize this, okay, with the charge density, you have to minimize it. This is what we saw yesterday also in case of Hartree-Fock equations. They take the energy functional and they minimize it, right? They do expectation value and they minimize with the psi or phi, whatever, put it to 0. And similar manner, this is also done. If you do this, you will actually arrive at here. These are the Cohen's-Sham equations which you can derive actually by minimizing this functional under some constraints. Let's say the total this thing, if you integrate the charge density, it should give the total number of electrons in the system. So based on that. So before we go to the Cohen's-Sham equations, so I just want to compare these two equations, equation number 1 and equation number 2. So if I'm comparing, what I get it is here. See, these two will cancel, these two terms. So we have to compare this one. There are only these 5 terms left. So from there, I try to find what is my exchange correlation term. So that is equals to the difference of the kinetic energy when the electrons are interacting and when they are not interacting. So this is your correlation energy, or you can call it kinetic correlation. And this term, whatever is this thing left, this is exchange. So this whole thing becomes exchange and correlation, which depends on your electron charge density. Okay, so now we will see once we minimize the energy functional, so we arrive at these equations where this potential is called Cohen-Sham potential. Now it has 3 things in it. So if you see here, this is V external, this one is Hartree potential, this one is exchange correlation potential. So now exchange correlation potential, you can actually calculate it from the functional derivative. So remember, I'm saying functional derivative. It's not the normal derivative. You have to see, actually there is a definition for this. You can actually check the textbook for this. So you actually get the functional derivative of the energy and then you get the potential. So you plug all these 3 numbers or these 3 potentials here, not numbers, plug here, solve these, and you get the see, the problem is that again, it's like you cannot solve this because there is an interdependence. For example, if I want to solve this equation, okay, so I need to know what is VKS is, the Cohen-Sham potential. Okay, but if I will know only the Cohen-Sham potential if I know what is my this thing is. See why? Because here Cohen-Sham potential, it depends here. You see this thing. It depends on the charge density. So if you want to know the charge density, you must know what is the wave function. Okay, these are the single electron wave function. It means that let's say we are dealing with the iron atom. So in that case, we will have 26 electrons. So you will have a 26 set of such equations. Okay, one for each electron. So that's what I mean by single electron wave function. So what I'm trying to say is, so before I can solve this equation, I must know this beforehand. So what we will do, we will start with a guess. So I'll take psi I, I'll make a guess, I'll plug it here, I will calculate these terms, what is the Hartree term and all, I will compute the full VKS, the Cohen-Sham potential, I'll plug it here, solve it again. So we will discuss in the following slides how these are done. Okay, and the orbital which you get in such a way, these orbitals are named as Cohen-Sham orbitals. Okay. And okay, so this is the like accuracy I want to point out. So before we go to that, you just please try to see these boxes. So the first, this one, so this is the Hartree-Fock approach. So see what they did is, so in the Hamiltonian which we have, there was kinetic energy term, right? There was external potential and there was Hartree term. And if you remember in the Hartree-Fock equations, there was an extra potential coming here. It was coming there, which we saw yesterday. That is the exchange energy. So this is what Hartree-Fock was able to capture. Now, when we move to DFT, what we saw, we actually now there is some fraction which is left here. So that is represented with this small rectangle here. You notice that, and this is the external potential, which is same as this. So this is Hartree potential or Hartree energy, which is same as this one, and here you have exchange term, right, which you have to get the, when you exchange the 2 fermions, you get the lowering in the energy. Okay, and this one is your correlation energy, which is due to the term which we had here, Ri minus Rj. Okay, and whatever is let's say you can't capture here, that term you add it here. So what I'm saying is this EC is actually equals to E kinetic when they are interacting. So this term I'm saying, this small box plus something which is due to many body effects or whatever. So that, so this full thing, so if you remember, if you are able to notice this, so please note the size of this rectangle. So this rectangle is slightly bigger than this one, right? Why? Because there is something extra coming here. Apart from the kinetic energy, there is also some correlation is still there. So if you sum this up, so this whole term is called exchange and correlation. Okay, so this is your DFT formalism. Now we see from this potential energy curve, you see this is the Hardy curve, which is only reaching here till here. Okay, and when you see this curve, this is the Hardy and Fock curve, which is able to reach somewhere here. Now when we use DFT, let's say GGA, we are able to go somewhere here, much lower than the Hartree Fock. But since there are some problem with the DFT, we can't exactly go to the ground state. This is my ground state, this dot. Okay, so still we are not able to reach the ground state. So the basically your DFT, it's the exact theory. So the only limitation which we have is to capture this thing properly. If we are able to capture this energy, the exchange correlation energy, we are done. So we can actually reach the exact ground state. Okay, and this term, the exchange and correlation term, this is also called heart of the DFT. It's like the heart is the main something like main organ of the body, right? Without it we can't function, right? It's the same thing here. If you include this properly, so if you are going like you don't read DFT or go blindly with the DFT, if you make mistake in choosing this function, you will actually, or the results that you will be getting, they may not be accurate in a sense that you are not at the ground state. Okay, so okay, let's understand what is exchange correlation energy. So see this picture. So from this picture you will see, so this is something like the, so okay, let me just tell you something. So why I'm putting it here. So we have nuclei here, okay, and there are electrons which you can say classically they are revolving around it, or you can say there is a charge density, a cloud after it, right? So there are chances that when the electrons come closer or when they go far apart, accordingly your wave function will, it may distort, right? It may, so there are chances that whenever you find the two electrons in the vicinity of each other, there will be more overlap of them. So there is a more chance that there is a density is more you say what I should say, it's like so this you can see from what I'm trying to say here. So there is a chance that the two electrons, when they are closer, the density is different. When they are far apart, then density is different. This is what this picture is trying to present. You can actually see this in terms of the charge density. Somewhere the electrons are closer, so this density is more here. Okay, and similarly, where this let's say this part is more or less uniform, you say the electrons are slightly far apart or something like that. So based on that, so it means that so now what we are doing, so this picture actually we have to capture. This is your exchange correlation part. Okay, now if you are able to calculate it exactly means exactly, nothing is left behind, so you are not missing any portion of it. So then you actually reach the exact ground state. But since we only calculate these things through approximation, so the approximation is you just take a small fraction here, you call it as a uniform electron gas, and similarly you take this portion, this is somewhere here, this is also like your uniform electron gas, and you keep calculating this small portion which is here, which is due to the homogeneous electron gas, and you finally average it out and you find out this thing. So this thing is here, this thing which we are calculating with the DFT. So this is approximated. So that's why please note these things here. I'm saying this is approximated, but this is what we have to know actually. So we can't know these things actually because we are relying on some of the approximations. So we were able to capture it, let's say to some, for a system, let's say there are many systems where the electron density is very uniform, so in those things the DFT is able to capture all the properties like structure or the total energy or something like your band structure. Those things are captured very nicely. But whenever you are not able to capture, because there are different kind of systems where electrons are interacting, somewhere you have d orbital, somewhere you have f orbital, in some systems you may not have d or f orbital. In that case, this thing will different, right? This term will differ. Your charge density will differ. So now, since we are using approximations, so you can actually what you can do, you can actually make your approximation better and better and better. So there are ways. So this is the usual thing which called LEA, which is local density approximation, where you just include your this local thing, which only depends on the charge density. Whereas if you go to the generalized gradient approximation, you see your this energy, the square which I'm showing here, it not only depends on the density, but also on the slope of density, the gradient. So this is sort of that is trying to capture the non-uniformity of the electron density. Okay, so you see that using different approximations, you can actually try to capture this exchange correlation energy in a better and better way. So there are many functions these days people are trying to propose. So the famous ones which people use, they are like PBE or like HSC. Those are the hybrid functions, and there are more like PW91. So these are there is like a full class of these sort of functions. So if you choose your functional intelligently and smartly, there is a chance that the properties that you will predict, they will probably match with your experiments or something like that. Okay. One more thing. So since we are not able to capture this thing, EXC, that will give you some problem. And also, apart from that, if you see the equations which we have here, this thing. So yesterday we saw that this term like this, EX plus there was some exchange. Not like that. Just a minute. So he wrote it something like that. There was Hartree term and there was exchange term. So what happened? The Hartree term has a self-interaction problem. Okay, and the exchange term was able to cancel that out exactly. Why exactly means, if this, let's say, Hartree terms give you something like -5, so this gives you +5. They exactly cancel out. But in DFT we have a problem here. We don't take the Hartree term in a similar manner as it is done in the Hartree-Fock equation. There is a different way to capture that. So because of that, the self interaction, it doesn't cancel exactly. Okay, in DFT. So this term, they don't cancel. Self interaction doesn't cancel exactly. So because of that, you don't get correct band gaps with DFT. So if you want to have a correct band gaps, so what people do is, they will do something like this. So they will take the some part, let's say 0.5% of the DFT, and rest 95% they will take the Hartree-Fock. So these are called hybrid functions. So if you mix these things and you try to get the, so there are you can also take not like okay, I wrote something wrong here. So it should be something like this, 0.05. Okay. So there are many approximations like where you can actually take it half and half. So you take half of this, half of this. So maybe you will get so slowly you will get the feeling. So how you can actually mix the things and try to minimize these things, self-interaction errors, and get the correct gaps. Okay. Okay. So this is how we do self-consistent cycle. So first you start with the initial guess of the charge density. You plug it here, you calculate this full. This is also called effective potential or the quencham potential, which is the external term, the due to nuclei, Hartree term, and the exchange correlation potential. Okay, you calculate all these, plug in the quencham equations, calculate the new wave function. So this is what I'm writing here. You start with initial guess, which is here. Then you calculate this, which is here, second term. Then you calculate new wave functions. These are the new, okay, after you put the pKs. And then now you have wave functions. So plug them here, calculate the new charge density. Now you see if this density, if it compares, like if it is equal to the density which we started with, okay, if they're equal, it means that the system is self-consistent. Okay, and that's how you get the charge density. Once you are done, once you calculate the charge density, you can calculate whatever you want. So once the density of the ground state is determined, all the physical properties of the system, they are determined. Okay, so only the ground state properties you can determine from DFT. If you want to calculate excited state or something, then you have to look for something else. Okay, and these are the references which I have used. Uh, so this is the very nice book. All the pictures which I have taken, these have been taken from this book, and this is also nice. So if you want to stay away from mathematics, use these three things, and this is the advanced DFT text if you want to go in details. Okay, with that I would like to thank organizers and